In traditional multiplication, when we multiply two two-digit numbers such as 72 and 19, we have to perform 4 multiplications in order to find the product. Here's an example. 9 times 2 is our first multiplication, and that equals 18. 9 times 7 is 63. Carrying the 1, 64. That was our second multiplication. Add a 0 for padding. 1 times 2 is 2, and 1 times 7 is 7. Those are our 4 multiplications. This one, this one, this one, and this one. We find the product by adding these together, and that's 1,368. Karatsuba's algorithm is fascinating because we can multiply 2 large numbers in less than big O notation. So for this example, with 2 two-digit numbers, we could find the product by only doing 3 multiplications. We can think of x as 72 and y as 19. We can further split this up into x1, which would be 7, x0, which would be 2, y1, which would be 1, and y0, which would be 9. We get the 7 from here, the 2 from here, the 1 from here, the 9 from here. Remember, we're trying to find the product of 72 and 19, or x and y, which can be expressed as x, y. And we can rewrite these using x1, x0, y1, y0 in the following way. Now this makes sense because x1 is the tens place of x, and we multiply it by 10 to the power of 1. Really, x0 is also being multiplied by 10 to the power of 0, but anything to the power of 0 is 1. So we can just simplify it to only be x0. Now, if we distribute this out, we'd get the following term. We'd get x1, y1, 10 squared, plus x1, y0, 10 to the power of 1, plus x0, y1 times 10 to the power of 1, plus x0, y0. Now we can further simplify these two middle terms by putting them like this. And let's multiply x1 and y1, which is 7 times 1. And then let's do x0 times y0, which is 2 times 9, or 18. Now if you notice, so far we've done 1 multiplication and 2 multiplications. What's left is another 3rd and 4th multiplication. So this isn't much faster than doing normal multiplication. In fact, it's a little bit more complicated. What Karatsuba figured out is that this looks very similar to what happens when you FOIL. So let's just show an example here. If we have x0 plus x1 times y0 plus y1, and then distribute that out, that's x0, y0 plus x0, y1 plus x1, y0 plus x1, y1. Now we've already figured out x0, y0 right here, which is 18, and x1, y1 right here, which is 7. And this, if you'll notice, is exactly this. So we can substitute this whole expression with x0 plus x1, y0 plus y1, which is what we started with here, minus 18 minus 7, or minus x0, y0 minus x1, y1. So we'll replace this entire term right here with all of this. Let's solve it first. x0 plus x1 is 2 plus 7, or 9. y0 plus y1 is 1 plus 9, or 10, minus x0, y0, which is 18, minus x1, y1, which is 7. Solving, that's 90 minus 18 minus 7, which happens to be 65. We only did one multiplication right here, but we still got this entire expression, which is made up of 2 multiplications. So Karatsuba's algorithm just cut one of these multiplications. Now let's substitute 65 back into this. It'll be 7 times 10 squared plus 65, which is all this, times 10 to the first plus 18. Solving, that's 700 plus 650 plus 18. And if we add that all up, that equals 1,368. Now we've just done Karatsuba's algorithm to solve a 2-digit times a 2-digit number in only 3 multiplications. Karatsuba's algorithm can also work for much larger numbers, such as 64 digits or more. And it can do it much more efficiently than traditional elementary style multiplication like we did here. This has big implications in things like cybersecurity, where it's common to multiply big numbers together. Now I'll show an example of multiplying bigger than 2-digit numbers. Let's go with 4,691 times 3,782. It's largely the same process. We're going to split each of these numbers in half. So x1 is going to be 46, while x0 is going to be 91. y1 will be 37, while y0 will be 82. Now it's also helpful for bigger than 2-digit numbers to define an m. M is how big each of the halves are. So in this case, it'll be 2 because there's 2-digit numbers in our x1. Now we're going to follow the exact same pattern, but this time instead of doing x1 times 10 to the first, we're going to do x1 times 10 to the m. In this case, it would be 2. We're going to multiply the first 2 terms, and that brings us to x1, y1 times 10 to the power of 2m. Then we add x1, y0 times 10 to the power of m plus x0, y1 times 10 to the power of m plus x0, y0. We combine these to be x1, y0 plus x0, y1, all times 10 to the m. And then we bring these down. Let's solve for x0, y0, which would be 91 times 82. And that equals 7,462. But you just noticed that we multiplied 2 2-digit numbers. This is something that we could have done recursively with the Karatsuba's algorithm. So I'll stop solving this problem here and just know that we could have done this exact problem like how we did in the first portion of this video. And we could have continued solving and recursively found the product of these 2 4-digit numbers and still less than big O of n squared. Now looking at the code here for Karatsuba's algorithm, the first thing you'll notice is here I have a multiplication table. And this is 19 by 19. And the reason for it being 19 by 19 and not, say, 9 by 9 is because we, yes, only multiply 1-digit numbers, but sometimes we add 2 1-digit numbers together and then multiply that sum. And if that's the case, the highest number that we could get is 9 plus 9, which would be 18. So here we have a 19 by 19 multiplication table, and this just is much more efficient. It's faster lookups, instant lookups. So rather than having to compute a multiplication, you can just find in this 2-dimensional array the product of any number. Under 19, that is. So this is our main function where we define x and y, which will be 72 and 19. And then we call Karatsuba. So looking at Karatsuba, we first split x1, x0, y1, y0. And this will give us the product of that, or the segment of our x and y. And as you can see, we just print it out here. It's also interesting to note that we're dealing with strings here and not integers. And so that's why we can do this sub and then find like half the length. You wouldn't be able to do that with integers, but with strings you can, and it's more efficient. We find z0, z2, and z1, which is the first, second, and third multiplications. This is not a recursive implementation. This is just an implementation that will only work with two-digit numbers. And the cool part about this, the Karatsuba's part, is that we find these two multiplications in line 33 and 34, and then with those products, we find z1, which is line 35. So this is the first multiplication, this is the second, and then this is the third. We print out z0, z1, and z2, and then we return, converting z0 into a string, adding 2 zeros at the end for the padding, z1 into a string, adding 1 0 at the end for padding, and then z2. And we sum that up, and that gives us the final product. So we can run it with z is 72 and y is 19. We get x1 is z, x0 is 2, y1 is 1, and y0 is 9. And then we find our z0, z1, and z2. And then we add them up to get 1,368. Now if we look here at the recursive implementation of Karatsuba's algorithm, we have the same thing. We have our multiplication table, and we have our main function. But looking into the Karatsuba function, we have obviously a recursive implementation. So here's our base case. If x is a one-digit number, y is a one-digit number, we just simply return the product, which we find from this multiplication table. Something different about the recursive implementation is we find m, which is the length of the number. So we find, I guess half the length. It's the midpoint. So we find the length, the bigger between the two numbers, and then we divide it by 2. So in this example, we have x is 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 7, 6, I guess, and then y is 5,678. So for this example, m would be half of the length of the biggest number. So this is the biggest number, which is 1, 2, 3, 4, 5, 6 digits long. So m would be 3, half of 6. Using m, we split x and y into their first and second halves, and then we print out the each of the halves, x0, x1, y0, y1. And then here we recursively call that with those halves. In this recursive implementation, I did this with integers and not strings, just so we could easily do arithmetic on them. So once we have the halves, we find z0 with the first halves, and then z2 with the second halves. And then z1, again, this is only our third multiplication, and we use z0 and z2 to find z1. You print that out, and then you combine them with similar logic as in the first code example that I showed you, and then we return our summed integer of the products. So we can also run this one, and you can see how our code is going about this recursively. So we start with the halves being pretty big, and then the halves get smaller, and then they jump out, get bigger, smaller, until we finally have our big z's. We add them up, and that is the product of these two numbers.